Magnets are objects that create a surrounding magnetic field due to their dipole nature. A magnetic dipole has two ends named north and south. The direction of the magnetic field moves away from the north and towards the south. If another magnet is within the field, forces will occur between the two magnets, still moving away from the north and towards the south. If the south pole of one magnet is near the north end of the other, the magnetic field will cause an attractive force between the two poles, as the magnetic field between the two moves from the north end of one to the south end of the other. Likewise, if two magnets had both north ends facing each other, then magnetic fields would be moving away from each other, causing a repulsion. If two magnets had like poles facing each other, oriented up and down, then this would cause one of the magnets to be lifted upwards against the force of gravity. It would also reason that the magnet would levitate in stability due to the cancellation of magnetic and gravitational forces. However, in 1842, Samuel Earnshaw proved that this is not possible mathematically because two magnets would create an unstable equilibrium, allowing one of the magnets to move and prevent the magnetic forces from canceling out the gravitational forces. There are some methods, though, that violate the assumptions made by Earnshaw and allow for a possible magnetic levitation. Electromagnetic stability, which uses electromagnets, and electrodynamic stability, which uses superconducting magnets, both allow for lift and stability and levitation and are used in transportation today.
Electromagnets are magnets where the magnetic field is produced as a result of running a current through wire that has been wrapped around a metal core. When current is supplied, it behaves just like a permanent magnet would. Electromagnets can be easily turned on and off and can also change polarity based on the direction of the current flowing through them. The strength of the magnetic field of an electromagnet can be increased or decreased as needed by changing certain factors, whereas the magnetic field strength of a regular magnet cannot be changed. Ampere's law states that the magnetic field around a closed loop is directly related to the amount of current traveling through the loop. By looking at a version of an equation for Ampere's law, the magnetic field strength for an electromagnet can be calculated. In the equation, the magnetic field strength B is equal to mu I n divided by L, where mu is a magnetic permeability constant that is specific to the material used for the electromagnet core, I is the current, n is the total number of wire turns, and L is the length of the coiled section of wire. By increasing the amount of current through the wire, by increasing the coil density of the electromagnet, or by using a core that has a higher permeability constant, the magnetic field strength of an electromagnet can be increased. The ability to easily manipulate strength as well as polarity of an electromagnet makes electromagnets very effective for creating the attractive and repulsive forces that suspend and propel maglev trains. So here we have an electromagnet that we will be calculating the magnetic field strength for based on given values. In order to find the strength of the field in Teslas, we must use the version of Ampere's law where B equals mu I n divided by L. In the question, we are told that magnetic permeability of the metallic core used inside the electromagnet, or mu, is equal to 2.26 times 10 to the negative third. We are also told that there is a current I of 5 amps running through the electromagnet and that the length of the coiled section of wire, L, is 0.25 meters. The only other variable needed is N, the number of turns in the wire, which can easily be found by counting each loop in the coil. When these values are plugged back into the equation, the magnetic field strength comes out to 0.226 Teslas.
The maglev train is a vehicle that uses exceptions to Earnshaw's theorem in order to levitate off the ground. Using the forces exerted between electromagnets, the maglev train is able to overcome the force of gravity as well as remove the resistive force of ground friction. Since the train now only has to face the force of air resistance, it is able to reach speeds well beyond that of a traditional train, with the latest trains being able to go over 600 kilometers per hour. Another advantage of the maglev train over traditional trains is that since it is powered entirely by electromagnets, no fossil fuels are burned into the atmosphere. There are two main types of methods for how exactly a maglev train is suspended. There's the German system, electromagnetic suspension, or EMS, and the Japanese system, electrodynamic suspension, or EDS.
In 1912, Émile Bachelet created a stable electromagnetic suspension using electromagnets by constantly adjusting the current flowing through the electromagnets. This violated one of Earnshaw's assumptions of constant current for an electromagnet in his theorem, allowing for stable magnetic levitation. The system creates a feedback loop, where the current is adjusted based on the position of the suspended object, thus altering the strength of the electromagnet and keeping the suspended object in stability. In 1934, Hermann Kemper used Bachelet's electromagnetic suspension to create a levitating vehicle, and is credited for inventing maglev transportation. Trains that utilize electromagnetic suspension have an undercarriage that wraps around a track guideway and use electromagnets on the undercarriage that attract to the electromagnets underneath the guideway. This attractive force is great enough to pull the train upwards against the force of gravity. In order to get around Earnshaw's theorem and stabilize the horizontal motion of the train, guidance electromagnets of like polarity are placed on both sides of the undercarriage, as well as the sides of the guideway, and are regulated by computers, keeping the train steady. Trains that use electrodynamic suspension use superconducting electromagnets on their sides and coils of wire in the shape of figure 8s on the sides of the track. When the superconducting electromagnets, which are much more powerful than a regular electromagnet, move past the coils, an induced magnetic field is created in the coils, where the bottom has a field that repels the electromagnet, and the top has a field that attracts the electromagnet, resulting in a net upward force that is strong enough to overcome gravity and levitate the train. Because the electromagnets must be moving past the coils in order to create these induced fields, the train cannot levitate while stationary, and requires wheels to get it moving to a speed that is fast enough for the train to levitate. A major advantage of the repulsive maglev systems is that they are naturally stable. This is because as the train shifts closer to one side of the track magnets create strong forces to repel the train magnets back to their original position. No feedback control is necessarily needed. Both trains that use electromagnetic suspension and electrodynamic suspension rely on the same method for accelerating the trains up to such high speeds by using what is essentially a linear induction motor. Electromagnets of fixed polarity are used on the front and back of each train car, where polarity is opposite front to back as well as side to side. The sides of the train track have electromagnets at regular fixed intervals, where the polarity alternates from magnet to magnet. Each electromagnet on the train is attracted to the magnet ahead of it and is also repelled by the magnet behind it, causing the train to be propelled forward. However, after moving forward, the electromagnet on the train would now be repelled by the magnet ahead of it and attracted to the magnet behind it, which would just make the train go back again. In order to keep the train moving forward, the polarity of all electromagnets on the sides of the track are flipped once the train moves forward, so that the train will always be attracted to what is ahead and repelled by what is behind.